we're getting into chapter 10, a culminating type of chapter for your year, because we are taking everything that you learned and now doing some complex three-dimensional figures. We're going to be finding surface area and volume. So the first, 4 sections of this chapter are all about surface area, and then the last whole chunk of the chapter is about volumes, okay? We'll have a quiz after we've done all of the surface area stuff. Today is pretty basic. We're talking about some definitions that we need to be able to use as we progress through. And so you can see we're talking about lines and planes. So you already know some things about these things, but a plane. Okay, so an example of this is the best example I can give you right here, right now. Something like this is a plane, right? So what would a definition be of a plane? This is not a true plane. Just like if I show you this, this is not a true line, right? But it kind of helps us sometimes think about lines, right? How is a true plane different from this? Hannah?
A plane is a flat surface that goes on.
Good, a surface that extends forever in 2 dimensions. 2 dimensions. So that's why using a paper or thinking about the whiteboard is a nice way to think of a plane. Extends infinitely in all 2 directions. So our next term is coplanar. Coplanar. So when you hear the planar part, there's the word plane again. So we're dealing with a plane, but co is the same prefix that's used when you are a co-captain on a team. So what is a co-captain? Right.
Well, there's more than one.
More than one. Okay, so if you're coplanar, what could you be? More than one and plane, what could you be?
2 planes.
You could be 2 planes. That sounds interesting. That's not what they're talking about here. When they're saying coplanar, they're saying, let's say you have 2 points. Where could they be? They could be, 2 points could be anywhere, but if they're coplanar, they would have to be where? Wesley? They would have to be, if they're coplanar, they would have to be on the same plane, right? So another definition would be sharing something. So I could have point P and point R, and they're on this plane. So they're coplanar. Okay? Coplanar is sharing a plane. I could also have 2 lines. Through point R, I could extend a line. Through point P, I could put a different line. And now I have coplanar lines. Okay? The next term that we need to know today is called skew line. And I don't really like that word skew because it sounds like ew. Ew. It kind of is ew, yucky kind of. I mean, when I think of lines that I like, what would you call these lines? If these were extending infinitely in both directions, what could we call these lines? Parallel. So that's kind of a pretty thing. And even in the word parallel, we've got parallel lines, the L's, right? And what would you call these lines? If perpendicular, they're forming what kind of angles? Right angles, 90-degree angles, so perpendicular, kind of a nice, handy set of lines, right? But skew lines are lines that are ew. They're not either of these things. They're never this, never, 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 parallel. They never intersect. Okay, so they would never share a plane. They're not coplanar. So one way I have to show you those skew line is, if we look at this, what shape is this? Rectangular prism. Good. Everybody say it? Rectangular prism. So down here I've kind of put a black edge here. Imagine it could go infinitely in that direction, right? Okay, so it's on this plane, the front face. It's also on the bottom face. It shares these 2 planes, okay? So where would a skew line be to that edge? I mean, could this edge here be a skew line? No, why not? Skew lines should not be parallel. These are parallel. Okay. Not only that, they share a plane, see? So they can't be considered skew. This line here too, this edge, imagine it went infinitely to be a line, would be intersecting this one. So again, that would not be a skew, right? So can anybody? So the opposite side and where? Would this opposite edge be okay? Would that be skew to this?
Yes.
No, why not? What can we say about this edge and this edge? They're parallel, so they're not skew. We could put a plane right through them, like a diagonal plane, you know, so they're not skew. So this front edge again, and what back edge is not parallel?
This.
These up and down, right? This one here. So imagine if I do it with my arms, it would be like here is one line, and here's another line. Will they ever intersect?
No.
Will they? Are they sharing a plane? Could they share a plane? No. And are they parallel? No. Now they don't have to be. These are kind of perpendicular feeling, aren't they? They don't have to be that. We could tilt one. We could tilt both. You know, it's kind of hard to imagine, but maybe it's easy to imagine. So a skew line. Here we go. So two lines that are not coplanar, never intersect, not parallel. You don't have to use a rectangular prism to show skew lines, but it is a handy tool. So we're going to do that now. So to draw, there's a number of ways to draw a rectangular prism, but usually you start with a front face, right? Sometimes if you're making a really long one, people go back and make that same clone on the back side. Let me make this a little nicer. Okay, but what we're trying to do is use dashed lines to show the hidden parts. Imagine it's a solid, right? So I'm going to show a side here that I know I can see by drawing a segment that's parallel and the same congruent to this segment here. I'm trying to draw a side that's parallel and congruent. These two sides should be parallel and congruent. Okay, once I have that, I can attach their vertices, their endpoints. So these are two sides I can see, and for this figure I can see the top as well. And so I want to have a vertex that is about the same distance from the upper left corner as the lower left corner was to the lower right to the lower right. Anyway, once you draw that vertex, you can attach the front top vertex and the back right vertex, right? So it's kind of a solid. So the other edges we're going to see are behind the figure, so we want dashed lines. So imagine there's a corner that's in the farthest most point behind the figure, right? It lines up with the front vertex and the far back and the top, all three. So it kind of gives you that 3 dimension. Somebody in the other class shared how Mrs. Sando taught you to do this in 3rd grade by putting a square and then kind of making its clone right here. And then just attaching all those common corners, all those vertices, right? When you do that, the only thing is you don't see the dashed lines, right? So it's a nice way to do it, especially with first grade. See how long you've been doing this? But you would maybe go in and like erase little pieces of the inside or something and show the dash so that you can get the illusion of it being 3-dimensional on a 2-dimensional paper, right? Okay, so to show the skew lines, we're going to choose a couple edges. We could do what like we just did. If I choose this edge, let's call this edge A, segment A. And so it could be skewed to maybe this side back here, this edge, which we could call B. So we would say segment A is skewed to segment B or something. They're not true lines because they have endpoints, right? When we draw a plane, we usually draw kind of the stereotypical slanted parallelogram, right? We're trying to represent something that's infinite, so that's hard to do. But usually a rectangle is not used. It's more of a parallelogram. And you imagine those sides extending forever. They're named using 3 points on the plane. The points are usually not in a line. They're not collinear to show, oh, it's taking kind of space up, you know, in 2 dimensions. So we have PS. We could draw a line through PS, but it could not be drawn then through C. You'd have to make a turn. And you could do that with any 2. You could draw a line through any 2, but not the 3rd. So we try to show 3 non-collinear points. So this plane is called PSC. You could name it any way you'd like to arrange those letters. And it's being intersected by line QC. See that? QC. Which means, is QC on the plane, PSC? Is QC, the line, lying on the plane, PSC? Yes or no?
Yes.
Who says yes? Who says no? Too bad, because it's not on the plane. Let me show you this. I'm going to turn on the video to show this. Okay, so imagine I have plane PSC. I have plane, in this case it's named PRZ. Anyway, imagine here comes line Q, QC, and there it is going through the plane. Okay, that's what that image is supposed to be showing you. You see a little dashed mark here behind C, and then the lower part of the plane there, and that's like the line is behind the plane, like this. Imagine you can't see the back of the pen probably from your vantage point, but you know it's going through. I can show you, right? Q is not on the plane PSC. So this is a line intersecting a plane at one point, and the point it's intersecting at is C. Okay? So when you see the dash, imagine it's going behind the plane. The intersection of two planes can give us something. And so let me show you with some paper here. Imagine I have two planes. I have a yellow plane and a blue plane, and they come and they intersect. What type of a figure do they form at their points of intersection? What? What are they going to form where they intersect? Are they going to form a plane, a point, or a line? Or are they touching at only one point? Actually, I see like a whole string of points, don't you see? Right? So they're forming a, what? A line. They're forming a line at that point, okay? So when two planes intersect, you have a line. Have other possibilities. Imagine, do two planes always have to form a line, or is there another way I could arrange them in space? Is there a way to arrange them in space where they would never cross each other? Chris? No, they're planes, so they're, by definition, they're flat, like a surface. Okay, so for two planes, we could have parallel planes, never intersecting. If not parallel, they will intersect somewhere. And when they do, they form a line. I'm not going to draw these, so too much to draw, but you do have images like this in your book if you wanted. I suppose you could print them, but this is showing a different combination of planes. We have three planes, red, blue, and green. And the way that these are configured, they're kind of slicing through each other. And how many points do they share in common, all three of these planes? Can anybody tell me in this one here, this configuration? How many points do they share in common? Do you see? Actually, the blue and the green share a line, right? But the red one doesn't share that line. The red and the green share this line here, but it doesn't share, the blue doesn't share that line. And the blue and the red share this line here, but the green doesn't share that line. So how many points in common, Wesley? One. This is a way to show three planes intersecting at a single point. Okay? Here, though, this reminds me of your book. If you picked up your book and open it up, the spine is the common area where all the pages are coming into, right? So what do they have in common here? Say it. I heard it. A line. That's right, a line. We could even have other planes here, couldn't we? We could have a lot of planes meeting at a line. Here we have what type of planes? Parallel, so they have no points in common. Because two planes are parallel here, there are no points in common for all three planes. And then this is another way to arrange three planes where they actually form, each plane forms a line with both of the other planes, but not at the same line. See that? So it's kind of a fun arrangement of planes. Okay, so for the intersection of three planes, we have these possibilities. And now you're going to use the information you've learned. Hopefully you'll be challenged by some of the questions to apply it in today's assignment, which you should have time to complete in class. Yay.
I'm like, the bone's right there, and then all my fingers